Hi, and welcome to this week's Inside Chips podcast. I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering, and I'm here with Charlie Janac, president and CEO of Arteris. The big story for the chip industry right now is everything AI, and the big problem is that we have a lot more data to process, a lot more data to move, and a lot more data to store. So what's changed on the data movement side, which is really where Arteris is focused?
Yeah, so AI is really about data movement. You're processing billions of weights. With ChatGPT, you're probably going up to trillions of weights. And you're moving them between the high bandwidth memories and the processing elements. And Arteris is a data movement company we're essentially the inventors of the network on chip. And we've had years and years of experience with high bandwidth on chip and chiplet data communications. And so as the importance of data movement in these chips grows, the Arteris solutions become more and more valuable.
When you think about generative AI, one of the big challenges there is that it's costing more per search than you're actually generating in revenue. In order to make this work, it has to become a lot more efficient, right?
Right.
So how do you get there?
One of the ways you become more efficient is you reduce the energy that it takes to move all of this data, right? So that's one thing. Another way is to improve the way the LLMs process the data. So there's a lot of innovations here to be done. And this innovation is necessary because right now, if you look at all of the data centers that are being built for AI training and inference, they are in the aggregate supposed to use 3 times more energy than the world has so far been produced. So there's a big market for small nuclear reactors. But one of the answers is that this whole thing becomes more efficient. And instead of focusing on just processing power, we're going to have to be focused on energy efficiency and energy utilization.
Yeah, it's really a recognition that power is finite, right? Because everybody's thinking we're going speed, 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 but that doesn't really get you to where you need to go with AI. You need to be able to do it within your power budget or it doesn't work. You've got, as you said, the AI data centers that are constrained by the grid. You've got power from a battery. And even in the case of inferencing, it's the same problem, right? So what are the big knobs to turn here?
One of the knobs is to start employing some of the power efficiency techniques that have been used in mobile, to stop using power when that power is not needed to accomplish the mission. And so that means turning things off whenever they're not being utilized, bringing them up very quickly in order to not impact performance, and just employ power management techniques that have been utilized in battery-powered systems.
In the past, this has been very difficult to implement or too expensive or too complex for most people to bother with. You think about a lot of the engineering teams, they just want to get their chip out the door as fast as they possibly can. They want it to work in potentially the power budget that they have, but that can slip a little bit. It really is all about performance. Are you seeing a big uptick in the adoption of NOx? Because this is one way that you deal with this.
Yeah, a network on chip is a more efficient way of transporting data, moving data. It's more efficient in protecting it. It's more efficient in transforming it. It's more efficient in delivering it. So all of these major applications are now using networking techniques inside the chip and increasingly between chiplets, which are making up a lot of these AI training and AI inference SoCs at the hyperscaler level.
What else can you do here? What else is missing?
Another major efficiency is the way you package the IP blocks. One is you need to have isolation between the IP block functions and the data movement, the network on chip. And you have to be able to standardize protocols, the way the registers are generated, the way it's connected, in a sort of a unified manner. You also need to be able to move RTL between the various parts of the chip in order to get design efficiency. The SoC integration automation is just a more effective way of applying the IP blocks to the overall processing and data movement problem.
And when you think about SoCs, those SoCs are being decomposed into chiplets now too, right? And going into advanced packages. So now you have even more connections because it's no longer just running through the body of the chip. Now it's running from chiplet to chiplet. It's running all the way around to the memories and back and forth.
Yes. The chiplets are making the system IP much more complex, right? You have to worry about hierarchies, right? Because the on-chip movement is one level of hierarchy and the inter-chip communication is another level of hierarchy. You have to worry about where to apply cache coherency most efficiently and where things should be non-coherent. Right now, the chiplets, they're sort of homogeneous. They're made by one company. Those are in production. But one of the things that's going to start to happen is you're going to have different companies making different chiplets on different processes and have to come together. And that requires a major evolution of the ecosystem of multiple companies in order to make that happen. And the data movement is actually one of the key things that enables such an ecosystem to be efficient and even to exist.
It also gets really complex too, right? Because now you not only have chiplets, you also potentially have higher usage of these chiplets than you did in the past, particularly with AI. And so now you need more redundancy that goes into here. You have to make sure that your signals are coming through exactly the same way as you expect them to.
Yeah, it's a complex problem. There's actually tools that don't exist today, which is, for example, we're on the front end, right? So we generate RTL, we're involved with architecture. But on these chiplets, there's also a bunch of physical effects. So for example, one of the very interesting opportunities is floor planning tools for chiplets, where you're trying to locate the chiplets in the most efficient manner in order to make the data communication work better with lower power and lower latency. So there's a bunch of things that still have to be developed.
And that floor planning is no longer just planar anymore, right? It now goes in 3 dimensions.
Yes. Yeah, you have both horizontal and vertical communication, and that increases the value of the system IP that can actually accomplish that by quite a bit. So the complexity of the data movement, the data communication problem in these kinds of chiplet structures is getting much, much higher than before.
Where do you see 3D ICs fitting into this, the real 3D ICs where it's a monolithic design?
One of the reasons for going to chiplets is that monolithic design is becoming very complex. Some of the very highest performance data center chips may have to be 3D designs, but many applications are about efficiency. We started off talking about power, and it may be more efficient from both design and from power perspective to have multiple chiplets than a monolithic design, because only some parts of the design really need to be on the leading edge process. So obviously the compute you want on your N2, N3, 14A type process or the Samsung equivalent. But some of the analog mixed signal is perfectly happy on a trailing edge process. Some of the memories would have a specific memory-oriented process, the SRAMs and the DRAM chiplets, FPGAs, those kinds of things. It may be more efficient for the mainstream design to utilize a chiplet approach, and only the very highest performance, sort of the peak of the and relatively small number of designs to be that complex, to be basically 3D integrated designs.
And these are the $100 million plus designs that are going in there, right?
Right. And there's not going to be that many of them. But the industry is going to decide what's most efficient. And our job is to follow what our customers choose, right? So if they choose to go integrated die vertical design, then we will follow that. If the mainstream is the chiplet designs, we will follow that as well. And our job is to have solution for whatever approach customers choose in order to implement their chips. So one of the things about the system IP, it doesn't set the architecture, it follows the architecture. And so it has to be highly configurable, highly flexible, highly efficient, and very flexible.
It's actually multidimensional too, right? Because you think about a complex chip at 2.5D, 3D IC, whichever one it happens to be, or 3.5D even, you've got all sorts of connections that are different speeds. You've got potentially different processing elements that are running at different speeds, moving data at a different rate. All that has to be taken into account, right?
Yes. So you need rate adapters, you need domain crossings, you need basically tens of network on chip functional blocks that allow you to manage the data. For some applications, you need functional safety because, for example, autonomous systems need to be pretty much fail-safe. There's an increased need for security where you want to be able to protect those kinds of systems from man-made attacks. So you need to be able to isolate successfully the various parts of the design in order to have power management, but also to protect the functionality. And because all these things have to connect together. There really is unlikely to be very many architectures for moving the data, because otherwise the industry is kind of suboptimized. So there's probably going to be 2 to 3 major vendors that are able to accommodate all of these data movement issues. It's going to take a lot of R&D. It's going to take a lot of scale. It's going to take a lot of support. And so we think that the industry is served by having 2 to 3 larger players that can meet all those requirements.
Well, in the past, a lot of the big chip companies developed their own NOCs. Has that changed?
Yeah, it's gotten very expensive. And so as you have to put in more and more R&D, you need to amortize that R&D over more and more projects. And if you're doing 5 projects or 3 projects, you're at a cost disadvantage against a company that's handling 100 or 150 projects a year. We see this data movement problem being increasingly outsourced because it's getting more and more challenging, more and more expensive. And the largest companies have the budgets to do it themselves. But it's also an issue of architecture, because if your system IP doesn't work, your chip doesn't work. And it's also an issue of keeping teams together for long periods of time, because while the processors change constantly, the processing elements change very quickly, the data processing infrastructure sticks around for quite a few years.
So this is all about movement of data on the very high end of the chips, these $100 million chips. What happens at the low end, the really small ones that have to do this inferencing and do all these other functions with very little power, probably on a battery?
The microcontrollers are getting much more complex now. You're starting to see microcontrollers with neural nets. You're starting to see microcontrollers with 32-bit processors. You're starting to see them with specialized functions, and they start to benefit from an efficient network on chip architecture. So we talked about moving upstream, right, into the high end, but we also see opportunities to add value on the lower end as these microcontrollers and IoT devices become more complex. And for example, you can have a design that has to run off of battery power for months. And for those kinds of designs, it may be a very small, simple design, but the power management architecture is extremely sophisticated, where you want to turn off even parts of the network on chip to conserve power. And only that particular part of the chip that's active actually gets to be turned on. So you have those kinds of sophisticated functions for specialized control functions.
And you also have, particularly when you start getting into the chiplet world, the commercial chiplet world, where you can buy chiplets off the shelf and be able to implement them in whatever your design happens to be. You now have the rudiments of the 80-20 rule, right? Or 90-10, where you say, okay, we can now set this up and we pretty much know how it's going to work. So put in another chiplet. We're probably not going to go that far off.
Yes, exactly. I mean, there is ultimately the dream, which is, I think we're several years away from this, is that people are going to be able to, there's going to be a sort of a chiplet marketplace where, reasonably standardized chiplets are going to be utilized, but then you need a very sophisticated, flexible, and low-cost communication infrastructure to accommodate those standardized chiplets.
There's been talk for a long time about building smart everything into these designs, and you really want those things to almost configure themselves. Where can this go? What comes next?
One of the things is that there is a shortage of system IP engineers in the world. When you're an electrical engineer, you go to the university, you study processors, you may study memories, but nobody has a double E in network on chip design or utilization. And so people learn on the job. And as these things get complex, the result is a shortage of experienced engineers in the system IP market segment. And so the only answer to this, besides more education and more awareness, is automation. There's obviously the answer is to expand the educational programs for this, but that takes a long time. So the best answer, at least in the short run, is automation. And so one of the things we've done is we've started delivering a product called FlexGen, which from several inputs such as floor plans, connectivity maps, location of the IP socket exit ports, and a couple other things, generate the NOC automatically. This is a boon for companies that are new to SoC design. It helps less experienced teams design great communication architectures for implementations for these chips. And so automation is another important aspect of delivering sufficient amounts of system IP architectures to satisfy all these chips that need to be built.
Charlie Janac, as always, thanks for a great explanation.